Hello everyone. This short video is going to discuss engineering requirements and how they apply to your engineering design. If you're in any of the ECE design courses, junior or senior, this is a great video to watch. This is going to help you understand why we take the time to make sure our engineering requirements are clear and concise. So why do we do this? When you're doing a project or making a design, you have many stakeholders involved. Each of these stakeholders can interpret the project in a different way, and unless you have a very clear set of criteria, engineering requirements, that everyone agrees to and everyone can agree have been met, you might end up with a variety of different designs, and you're going to end up with some unhappy folks when the design they envisioned isn't the design that you finally produce. There's two types of requirements. There's customer requirements, sometimes called marketing requirements, and engineering requirements. Customer requirements are often vague or broad, though they can be very specific, like an engineering requirement. But engineering requirements are always verifiable, unambiguous, abstract, and traceable. If they do not have those four traits, an engineering requirement is not yet ready to be called an engineering requirement. From here on, we're going to talk primarily about system-level engineering requirements, but you can apply these same concepts to subsystems or even block-level requirements just to make sure that you have defined those requirements very well. So let's talk about verifiable. It's very important that an engineering requirement is verifiable. If you say that a system must be small, that's great, but you don't necessarily know how small is small. Okay? If you say that a system is better than this or better than that, you have to have a way that you can prove that to every party involved, every stakeholder involved. So looking at one of these as an example, the system must be cooler than a Tesla Model 3. So the term cooler is the problem here. Cooler, in this case, could be literally temperature, or it could be aesthetics. It's awesome, it's better than something else. Assuming it's an aesthetic challenge, the system will be rated as cooler than a Tesla Model 3 by 9 out of 10 people. This is verifiable. In the first example, how many people do I have to ask? Who is the metric? Who defines cooler? In this case, we said 9 out of 10 people. Now, the term people might also be ambiguous based upon the situation, because, for example, we might only care if it's rated cooler by engineers, or it's only cooler by children, or it's only cooler by... so the definition of people could also be at risk here. Looking at unambiguous. This is an important one because you want to be sure that if you read the requirement, two different people reading it don't have a difference of opinion about how it is to be met or if it has been met. So in this example, a bad system requirement, the system will operate normally without failing. So the problem here is what is normally, what is failing, and how long does it need to do that? Indefinitely? So another example could be the system will perform the functions of measurement and transmission, that's normal operation, of data, with no more than one lost data sample for a 1 hour period. So you're accepting that there's going to be some loss of information, and everyone's accepting that loss of information. And you're saying how long it'll work over that period of time, 1 hour. Otherwise, we can assume it has to work forever, and you would have to test it forever, and that's not very practical when doing an engineering project. When dealing with abstract, we want to be sure that our engineering requirements specify operation or function or performance or safety or so on and so forth. We'll talk about those different areas here in a second. But that when it's specifying those, it doesn't specify exactly how the system will accomplish that. If we make it specify exactly how the system will accomplish it, then if we choose a different design option, say for example switching from a lithium polymer battery to a lead acid battery, as we'll see in a few seconds, then we have to rewrite the requirement, which means we have to get every stakeholder involved, we have to get everyone to approve the new change, and that opens up opportunity for stakeholders to want other changes, which can be useful and important, but we don't want to have changes willy-nilly. That's an important thing to point out. Engineering requirements are designed to be changeable. You can change them as you learn new information, but there's a process. You can't just change it willy-nilly last second. You have to ask your stakeholder, all the stakeholders that are involved. You have to make sure everyone agrees, and then you can make the change. And that process takes time. So you should never expect to change your requirement on the fly. Back to this example, the system will use a LiPo battery to have a runtime of greater than 24 hours. In this case, specifying LiPo batteries is probably redundant, so a better example would be the system will run for at least 24 hours on a single charge. That still implies there's a battery, hence a single charge, but you're not specifying the chemistry. This does bring up an interesting thing. Sometimes you have constraints. Your stakeholder says you have to use an LM555 timer chip. In that situation, great, you still have to use it. That's a constraint. It's not a requirement. A requirement has an ability or in a requirement, you can exceed it. You can do better than. In this case, you could have something that ran for 48 hours, but you have to at least do 24. In the 555 timer example, you just have to use it. You can't be better than a 555 timer and meet the constraint of you must use a 555 timer. Finally, requirements need to be traceable. This means that the engineering requirement needs to be obvious where it came from. So if you have a customer requirement of must be small, your engineering requirement would be must be 10 by 10 by 10 centimeters. Those two being connected make them traceable together. Requirements are going to come from a lot of different categories. They could come from performance, functionality, manufacturability, usability. They could even be political in nature because you have to meet some certain goals for a group of people. So these categories are pretty important in that most projects you'll do will need to have requirements from at least a few of these categories. If all of your requirements are performance requirements or all of them are operational requirements, you're probably going to have a system at the end that doesn't really represent what all of your stakeholders are interested in. So remember, your stakeholders are both your physical stakeholder from the external entity or internal entity. They're your instructors, they're your TAs, they're users of the system, whether you know who they are or not. And all of these people need to have a system that works for them as much as possible. So try to draw requirements from multiple different categories. All right, so let's look at an example. In this case, customer requirement, the system must be small. I've mentioned this one a couple times. What's wrong with this? Well, the problem is what the heck is small? Is it a measurement of weight? Is it a measurement of size? Is it smaller than a bread box? Define small. And without knowing anything else, you can't. Now, if I tell you that you're building a wristwatch, I can get an idea for what small is. If you say I'm building a car, I can also get an idea of what small is, but they're very different ideas. So an example of a good engineering requirement might be the system must be less than 10 by 10 by 10 centimeters. That's measurable, so you can prove it, and that's important. What category might this fall under? So for me, I think this category is probably best under function or performance. So if it has to fit into a specific space, it would be a functional requirement. If you want it to be small because you're going to sell more of them if it's small, it would be a performance requirement. Let's go ahead and look at another example, and we'll take a few moments for you to think about this one. The system should have high quality audio. What could be a good engineering requirement for this, and what category might it fit under? All right, so you've had a second to think about this one. So a possible engineering requirement for this could be 9 out of 10 listeners should rate the audio as high quality as compared to the same music played through a JBL Flip 3 Bluetooth speaker. So what did we do here? Well, we tried to establish a standard. In industry, working with audio, there are a lot of standards that you could make your system meet. However, here at OSU, we may not have the equipment necessary to perform the tests to verify that. We're not going to be able to approve your system as Dolby quality audio. We don't have the tools or the equipment, and it's expensive to do that. In fact, it probably takes a third-party reviewer to do that. So we have to kind of be a little creative. In this case, we've established the Flip 3 Bluetooth speaker as the standard that we want 9 out of 10 people to say our system is better than this. That's fine. In this case, the category I would probably say is performance, because you could do better. You could get 99 out of 100 listeners to say it was higher quality. So it's definitely a performance requirement. So what's your takeaway? Engineering requirements need to be verifiable. Okay, can you actually prove it? Traceable. They need to be derived from a customer requirement. Abstract. They shouldn't describe exactly how your system or your internals work, and they need to be unambiguous. Two different people reading the same requirement would not have a difference of opinion about whether or not the requirement has been met.